Okay, let's get started. So the mic is not working. I made some video with my laptop. I hope that it works out well. Sorry for the bad quality. Anyway, so today I would like to kind of wrap up what we have seen in topology and also give some hints along the way what we would like to do with respect to the exam, what kind of good exam preparations, wrapping up all the whole story, and kind of there will be a list of questions, and it's kind of good to kind of solve them for some examples, and then you're really well prepared for the exam, and hopefully eventually the exam will all be over, and we'll have a good, some kind of nice view back on topology, and it was actually pretty cool. That's what I hope. That's what you will think after the exam is over. But of course, more practically, as I said, there will be in green exercises on the slides, which I highly recommend to do. They will be very useful for the exam, I promise you. Anyway, so we clearly had 3 topics, and we will go through all the 3 topics. So the first and the second one were a little bit interlaced. So we started with graphs, went to surfaces, and got back to graphs again. So we will do exactly the same here. But then the third topic was, well, it was also interlaced with surfaces. There was alpha surfaces and so on. But it was more like a topic on its own. But we will see all of them in this lecture. And the takeaway message for all of them is really that, first of all, I personally feel like it's really cool. It's a really cool part of mathematics. But it's also very useful. So a graph, the main example of a real-world graph is the brain. And people really do that, and I really found a nice picture here. So they really map the various neurons of the brain into a graph. The graph is so huge that you can't even see the edges, but you see kind of clustering of the vertices here. And then they study the brain using graph theory, which is ridiculously amazing. So exactly the kind of the type of methods I will recall, so that the ones we have learned in this lecture. Very similar for the surfaces. So people use the topology or the combinatorics of the surfaces to study something like the geometry of the universe, and it's still not kind of not settled what the geometry is, and I show you later actually why that is so hard in a more practical version down to earth on surfaces. And knots are also very applicable. I showed you the picture of the DNA knotting, and they really table all these knots. We will see knot tables as well. Knot tables are very important. And it's just really amazing how applicable actually everything I told you in the end actually is. Okay, so let's get started. So first topic were graphs, and there was an abstract definition which I will never come back to again, but essentially a graph is a collection of vertices and edges, and they are put together into the graph with vertices and edges, and all that matters is the picture kind of you see, kind of the connectivity between the various vertices. So a graph is about connectivity. Surfaces and knots have different flavors. So graph is about connectivity, so we don't really compare graphs to all the others. And the correct notion for graphs for equivalence was isomorphism, which is just saying that the bijection of sets preserving the connectivity within a graph. And I list here a few questions, and we go through all the questions today, and that's exactly what you should kind of have in mind if you think of an exercise. You just pick out your favorite graph and just run the machinery from 1 to 10. Can you answer them for your favorite graph? So the first question you should always ask is, have I seen that graph before? Maybe we have met it before, maybe it appeared somewhere, maybe it's one of the standard ones. We will see the standard ones in a second again. I mean, that's really important information if that happens, because we know quite a lot about the standard graphs. And the standard ones were just a line. We'll see them again in a second. The path graphs, the lines, cycles, the complete ones, and the complete bipartite ones. So it's always a good idea to kind of check, to eyeball, is my graph any of those? Then, because then all of the other questions are much simpler to solve anyway. And another thing we always want to do is we always want to have a good handle on the number of vertices and edges. Of course, we want to compute the Euler characteristic in the end, which for graphs was just vertices minus edges. So we kind of want to know those numbers, and eventually that will come out as a count, which is not really hard, obviously, counting, but maybe a bit painful the bigger the graph is. Related, obviously, I already said it. We always should check the Euler characteristic of a graph. It's very useful. For example, there will be statements, Euler characteristics, and trees. So Euler characteristic 1 for a connected graph is equivalent to being a tree. A very, very simple check what a tree is, and so on and so on. Is a graph connected? That's a question we usually can eyeball, but we definitely want to answer very, very early on. So we do have connected components, meaning, so connected just means you can go from every vertex to every other vertex in the graph itself. And you should just count those numbers, right? So it's very important information. So I just list a few numerical datum we want to get here from graphs. The other thing we have seen is a very particular type of graphs. So maybe the first 4 questions is kind of in general, and then maybe we want to think of various types of graphs. There are trees. Can we write down a tree? We'll show you some nice trees in a second. So can we find down specific types of graphs? Can we find down Eulerian graphs? Remember, Eulerian graph is something that has a Eulerian cycle. It's a very particular form of a graph. Not every graph satisfies that. So it's good to know whether a graph satisfies this property or not. Related, of course, kind of count the paths. What are the paths and how are they related? Can we find circles and so on? And so this was kind of the first part. So we did that in kind of week 7, if you want. And later we came back to it asking a slightly different and more topologically flavored question about embeddings of graphs. So the baby case is can you draw it in the plane? We'll see more examples in a second, but then maybe more beefed up. Can you draw it on other surfaces? Can you draw it on torus? Can you draw it on a Möbius strip or whatever? And related is, we call this coloring question of maps. And I will show it to you for a specific graph. So graphs, funnily, have always some funny names. So if you go on the Wikipedia, for example, the list of graphs, and you find whatever, 100 graphs, and they have some names. And essentially what I did for the exam is I picked out one randomly, and you should run essentially this list for this graph. And here we're doing one of them, which I also picked out randomly, and it's called the Pappus graph. Okay, so let's recall what these actually are. So the first thing really is to compute edges and vertices, compute the Euler characteristic, really, really important notion. And the Euler characteristic for a graph is only vertices and edges because we don't know what faces are. For a general graph, what is a face? Exactly. So we don't know. We just compute the Euler characteristic. And I've listed 2 examples here for you. So a connected graph upstairs with Euler characteristic -2 is telling us it can't be a tree. And obviously you can see it's literally not a tree. So if I haven't miscounted, it should have 8 edges. And I labeled the vertices, so I'm pretty sure there are 6 vertices. And yeah, so remember that for something like the degree, the funny loop counts twice. So the degree of vertex 1 here, for example, is 4. And we had various combinatorial numerical ways to relate various notions in the graph. We had this handshake lemma, the degree formulas for vertices and edges and so on. So there's various things you want to do with them, so you definitely should do that first. And it's usually a very, very simple exercise for the graphs I'm going to show you. Obviously, if you have a graph with 1 million vertices and 1 trillion edges, you need to come up with some good way of counting. But a computer, for example, can do that really simply. But for the graphs I'm going to show you, never have too many vertices and too many edges. It's usually just, you can just eyeball that question. And what I'm trying to sell here a little bit is most questions I'm going to show you in the exam, you can eyeball them. So whenever you can do it, just think about it for 20 seconds. Maybe I can solve this question without doing any calculation at all. I'll show you some examples of that as we go along. So here are the standard graphs. It's usually pretty easy to decide whether a graph is a line. It's usually easy to decide whether it's a circle. It's very easy to decide whether it's complete. Just look at the neighbors. It needs to neighbor everything. Complete bipartite is a bit trickier. So you need to kind of color your vertices and then check whether, color your vertices, whatever, blue and red, and then check whether everything is connected to everything. But we have a lot of formulas for those guys. So if your graph happens to be one of those, you're pretty good. So we have just a list of formulas that we had, like the number of vertices, the Euler characteristic, and everything is just given by a formula. So that's really the optimal setup. Your graph is one of the standard ones. Graph theory would be very boring if your graph would always be one of the standard ones. So most of the time it's not. But you should definitely check first. So if I show you this picture here, you should immediately think, oh, this one is a cycle, and this one is, what is it, the K4, the full graph, the complete graph with 4 vertices. And you should just then, we have seen everything for them. So we know, for example, that the complete graphs are planar if and only if the number of vertices is smaller than 5, so strictly smaller than 5. So this one actually should be planar, sorry. And this is not always obvious. Remember, let me just show you the picture in case it wants to load. So this is a planar graph, but it's not always obvious from the way you draw it. But for example, if you would have identified already it's K4, you know immediately it's planar. You don't need to do anything anymore. We already had that. And sometimes it's really tricky to decide. So here we just redirect one edge. But think about this really huge graph, and it's kind of messily embedded in the plane. So messily in the plane, the diagram is very messy. It's not easy to decide. So it's really, really good to have an idea what type of graphs you see in front of you. So here, again, you should immediately think, oh, that's a cycle, and that's K4, so we actually know what to do with them. We immediately know that G is a subgraph, for example, of H, and that G is not a subgraph of H, because it has too many vertices, so how can it be a subgraph? But H is planar, because Kn's are planar if and only if N is 1, 2, 3, 4. So this is really good. So if you end up in this situation, it's always, always really, really good. The next thing you should check is whether your graph is a tree. And a tree is really a special type of a graph that comes without cycles. So here, that's a definition of a tree. So whenever I ask something about a tree, that's the definition of a tree. It's an acyclic graph. So acyclic means without cycles, so cyclic means you have a cycle like here, the little one in orange. And trees are really amazing class of trees. Trees are a amazing class of trees, obviously. Trees are a amazing class of graphs. And for example, you can always run this induction. Remember, there was this really crucial statement about trees. You see it here very nicely in my trees from chemistry, the hydrocarbons. And there was this notion of a leaf. So every tree has at least, if it's not completely silly, has at least a leaf. And here the leaves are the hydrogen atoms. And if you take one away, you get a smaller tree, and you can run induction. That's, for example, how we proved this corollary. And you should try that yourself, because it's just the main property of a tree is that it's kind of easy relatable to smaller trees. So, and by the way, chemically speaking, all of these are very similar, and as you can see, graph theoretical, they're also very similar. And again, kind of real world goes very nicely hand in hand with, well, mathematics. Another property we have seen is this crazy property of being Eulerian. Let me show you a Eulerian cycle. So it's really hard to actually find them. So here, in this projection of a graph, so in order to make it visible, it's kind of stepwise how the cycle goes. So you start just in the middle and go out, and there are many of them, but they're pretty hard to write down in practice. So if I ask you, really, I won't do that because it's hard, but if I would ask, or someone would ask you, write down a Eulerian cycle, that's really hard. You should be a little bit afraid. So that's really hard. A computer can do it, so it's not that bad, but do it by hand is a bit tricky. But surprisingly, just the question whether there is a solution at all has this ridiculously simple statement here. You just need to count the degree at each vertex. And if it's even, maybe I shouldn't have closed this. If it's even, then it's always good. So here, the only thing we need to check is that every vertex has degree 4, as you can see. So we don't need to run this. We just already know by Euler's famous theorem that this is Eulerian. And that's kind of a type of question you could ask, right? So is this graph Eulerian? Just check it by eyeballing the number, the degrees of the vertices. Here it's 4, so everything is 4. so everything is even, and so this theorem, this beautiful theorem actually applies. Say it again. The theorem is really simple. It's very powerful, but it only tells you whether something is Eulerian or not. It doesn't give you the corresponding path and the cycle. And there was a similar statement for the paths, which I'm not pulling up here, but essentially the same statement. Just you have a start vertex and the end vertex, which can have an odd degree. So again, very powerful method to do it. And the last topic we had were those embeddings, and this crazy formula, which I will plot for you in a second, or which I have plotted. It's actually, so the formula, I ignore the integer part here, behaves like this. So for big Euler characteristic means easy surface. Small Euler characteristic means hard surface. So the smaller the Euler characteristic, the more colors you need. So you start with the famous 4 here, and then it goes up like square root curve. So it gets more complicated. You need more colors for more complicated surfaces. And that fits very nicely to the following. So the easiest surface is our good old friend, this one here, the sphere. And the easiest form of a graph to be embeddable is planar, which means it embeds on the sphere. And if it embeds on the sphere, so it's somewhere here, I don't know, here's my little graph, somewhere locally on the sphere, it will embed into any surface, because we already know how the surfaces look like. They are spheres with kind of extra decorations, like a handle or something. But my little graph here still sits locally on my sphere, so it perfectly goes well into all other surfaces. No problem at all. And the formula tells you that this should be true, because those graphs need a small coloring number. So where is my, it's here, need a small coloring number. So in easy surfaces, everything with small number goes in easy surfaces, everything with needs a high number goes in more complicated surfaces. And the point is, if it goes into a torus, it will go into a torus with, into a surface with 2 handles. Because locally, you just need 1 handle, so whether you attach another handle doesn't matter. It goes into a surface with 50 handles. So this is really kind of a complexity measure of your graph. So that was one of the questions in the test exam. So if it is planar, it automatically goes into any surface, no matter what it is. I just was drawing it, one with a handle here because that's the easiest one to draw, but it also goes onto a projective plane by the classification formula. And it's kind of all hidden in this crazy formula of Ebel's, which is really, really amazing. Okay, so let's run this for this graph, and roughly a graph of this form will appear in the exam. It won't be this one, obviously. But you can kind of already see that it looks reasonably complicated, so maybe we just run our little game here. So counting vertices and edges is really not hard. If I haven't miscounted, those are the numbers. So the Euler characteristic would be minus 9 here. It's just an exercise. In particular, if it's arranged on a circle, you can count the vertices pretty easy. And in this case, everything has degree 3, so you can actually get the edges just from knowing how many vertices you are by a little calculation. You can also count them. And it's clearly not a standard graph. I mean, no way. So the degree is way too low, for example, to be a complete graph. So that's a bit disappointing, so we really need to go through it. It's also clearly not a tree. So here, Euler characteristic minus 9 tells us that it's clearly not a tree. Okay, but we just can run our machinery. So note the following. So you can kind of eyeball in what kind of surface this guy embeds by looking for the smallest cycle. And the smallest cycles that are here in color, they're always of length 6. So you probably need a hexagon somewhere, and by Hewlett's coloring formula, this means that probably the smallest surface which this one embeds into is actually the torus. So you can also eyeball kind of in what surfaces the thing embeds by counting the smallest type of cycles. So here the smallest type of cycles are hexagons. They're very strangely arranged in the graph. And the Eulerian question is very easy to answer here. Everything is of degree 3, so the graph is dead no matter what we do with respect to Eulerian cycles. So here it just can't work.
How did you know how did you know it embeds in a torus?
No, I'm just saying. So you'll see the picture in a second. Let me come back to the picture. But it's a good way to kind of check what would be a good surface to embed it to. I just look at the smallest cycle. So the hexagon is associated to, here you go, to the torus, because it really gives you a nice paving of the torus. See another picture again. So this is the graph of the torus. I don't expect you to do that yourself. The point is hexagon means torus. So when you see a hexagon, it will be the torus. Smaller things are usually planes. And that's, if you run the Euler characteristic argument that we have run in the lecture to show that something is not planar, it essentially boils down to you look at certain polygons with a certain number of edges. Hewitt's formula here gives 7, so this is an example where Hewitt's formula is not optimal. So this doesn't embed into the plane, it's not planar, literally because they are only hexagons, and you can already see it. If you pave the plane with hexagons, it will be infinite, so this can't work in a finite way. You can run an Euler characteristic argument to check that, but the point is you can also eyeball that immediately. It can't be planar, there are too many hexagons. Anyway, so Hewitt's formula gives you 7 for the torus, but you might need a fewer number of colors. So this is an example that only needs 3 colors actually. So Hewitt's theorem is far from optimal for certain graphs. It's just the maximal number you need. And the one I would like to do is an exercise, exactly the same pattern. It has all hexagons, and it was this picture where you really needed 7 colors. So this has no chance to be planar at all. Again, just really try this yourself. Run exactly the same questions. Count the number of vertices, count the number of edges. Is it planar? Is it Eulerian? Is it a tree? Whatever. Just do it, and it will be very useful. So that's kind of what we have seen about graphs. So to answer your question, it's actually really hard to decide what the minimal surfaces a graph embeds into. What I'm saying is, for a lot of graphs, you can actually really just eyeball it by looking for the longest path. The smaller the path, the easier the surface. So here again, the smallest path is 1, 2, 3, 4, 5, 6. It's exactly one of the hexagons you see on the right-hand side. Okay, second topic were surfaces. And I think what got a little bit lost is the connection between the polygons and the surface itself. It is really useful to have, at least for the standard ones, this picture in mind how they are created. And I show you some of them again. So this is here how actually the Klein bottle comes from folding this piece of paper, the standard form of the Klein bottle. We'll run that several times. So it's good to have that in mind. Again, you can eyeball quite a few questions by just knowing how that works. It's essentially the same type of questions we ask. Have we seen it before? There are the standard ones, which we'll see on my next slide. Can we count boundary cycles? Can we count its Euler characteristic? Can we check it's connected? Can we check it's orientable? What are polygon forms? What is the standard form? Always look for the standard form. Right? So this is kind of the DPT guy. And it's very useful. As soon as you have those 3 numbers, you have identified the surface completely. And then you can answer all of these other questions. So cross caps is P, handles is T, and boundary cycles is D. And in the case, what is a chromatic number? So what does Hewitt actually tell you for the corresponding surface? Keep in mind, the smaller the Euler characteristic, the more complicated the surface actually is. And you see that from the formula that we will show in a second again. So really, I really encourage to have a good geometric picture of at least those ones. Maybe we take out the projective plane, which is really hard to imagine, which is usually better in the polygon form. But for example, for a torus, we had this slightly nice picture, which we just really wrapped the torus. So this is a torus as a polygon. It's just a square, and you identify the edges. And exactly what happens is you first put it into a cylinder, and then you identify the other 2 edges, and it wraps up into a torus. Okay. And if you can do that on a polygon, somewhat in your mind, which is really, really useful, then you can identify surfaces pretty easily without running any algorithm. There is an algorithm, we will run it again, and it's definitely useful to know it, but often you can just say, oh, this is the torus, or whatever, this is a projective plane, or whatever. If you just keep in mind that this is all about folding the polygons into surfaces. The sphere, how do we fold the sphere? You just take the paper, clap it together at both sides, you get a sphere. Klein bottle was a picture from before. Möbius strip, do I have a nice one for the Möbius strip? I certainly do. So the Möbius strip is here. So it's this, so do you start? Yeah, there you go. That took quite a long. So the Möbius strip is this non-orientable surface that you get by taking the piece of paper and just wrap it around so you get a little twist. And non-orientable meant that it has just one side. And as you can see here in this nice animation, the ant just goes around all the way, and it's the inside and the outside at the same time. So non-orientable was this one-sidedness. And you again can eyeball that very simple on the polygon, because it's just exactly like here. It has two edges that go in the same direction if you read just in counterclockwise order around the polygon. So really have some geometric picture of those in mind. They're just the basic building blocks of all surfaces. Again, really, annulus is really simple, and this is really how it works. So here, the points we usually identify, x will be a point here, and y will be a point here. And you wrap it around the cylinder, you can already see that this little b here, if I identify a and a, will wrap itself up into a little boundary component. And that's why we are counting all these things. So that's why the three edges will be a little circles in the in the surface. So it's really useful to have all of these pictures in mind. The boundary, just to make this clear, so what is the main point of surfaces? A surface is something where everything locally is a disk. Say it again. So that's why planar means everything locally is a disk. So shrink your graph onto a little disk, put it anywhere, and it actually embeds into any surface as soon as it's planar. And the difference between a boundary and regular points is that on a boundary you have those little half disks. So there's only a half disk. For all other points, there are disks. So boundary circles are really harmless. In the picture, here are 4 boundary circles. Can we find them? They're the holes in the surface. 1, 2, 3, and there's an outside hole, which is a bit hard to see, but if you think of this as being a sphere, and we poke the hole and just bend it open, that's why you have an outside hole here. So the holes in the surface are actually the boundary cycles, and that's why we kind of always try to find them in the description, and I'll show you in a second how you could think of this geometrically, and maybe that makes more sense. Again, many different, wildly different polygon forms for the objects. The standard one for a torus can look wildly different. So we kind of want, in general, a method to tell them apart, and the way to do this is Euler characteristic, because the Euler characteristic is independent of the polygon form, right? So many polygon forms for the same surface, but the Euler characteristic is attached to the surface. So it's an invariant of the surface. Many forms, but every form spits out the same number. It's an invariant of the form, so we should compute it, and the computation is usually very simple. So let's do that for both sides here. So here's just one vertex. Here are 2 vertices. You can try to see that if you want. But certainly you have 2 edges, and here you have 3 edges, and you have 1 face. And as you can see, the calculation comes out as the same, although one of them looks like a hexagon, and the other one looks like a square. Euler characteristic, always compute the Euler characteristic. Same goes for graphs. Always compute the Euler characteristic, because it's a good hint what kind of surface you have. So if you get Euler characteristic 0, it's quite likely that it's actually a torus. It's not guaranteed. So that's why we beefed up the picture a little bit. So here's an example. So the Euler characteristic of the torus is 0, but the Euler characteristic of 2 tori, just here's a torus, they're not related at all, is also 0. So we can't, just from the Euler characteristic, we can't distinguish one torus from 2 tori, which is not perfect. But what we need to do in order to fix that is to check by before whether it's connected or not. And obviously for two tori, it's very easy to check that they're not connected. Torus has order characteristic 0, Klein bottom has order characteristic 0. They're not the same surfaces. And what is fixed here, you need to check for orientability. So in the word for T, you don't have any edges pointing in the same direction. In the word for K, you do. So K is non-orientable. Let me try to convince you that it is actually the case. So again, the same picture. Non-orientable means it just has one side, and my little ant here is on the outside, but it can also go into the inside. So actually, the outside is the inside, and it will come out again. Eventually, just go all the way around again. So it's just a one-sided surface, and these are the non-orientable ones. There you go. On the outside again. Very strange objects, but they exist. And on the polygon, it's very easy to check. It's, in this case here, those two edges point in the same direction, so A and A. So it's not orientable. So although the Euler characteristic is 0, orientability checks that this is true. And there's one more thing you need to check. So it's always connectivity, orientability, and the boundary. So Euler characteristic of the torus again 0. Euler characteristic of the annulus is 0, but we have seen the annulus already. So no, here it was. So it has two boundary cycles. The torus has none, so they are not the same. And then you're actually done identifying the surface. So you only need to know Euler characteristic and those three. First one easy to check. Second one is usually also easy to check. And third one, I try to convince you that it's actually not so hard to do. So let's just do it for. Let's just go through it. So connected is really simple. You just look at the polygon, and here they're connected. Oops, that was way too bad. They're connected by going through the edge C. You come out here again. So this is a connected surface. And the other one here is not connected, so no matter what you do, you can't go from here to here. So first thing you check is whether my surface is connected. This is really easy if you just have one face, then it's obviously connected. But for many faces, it's also not so hard. You just play this game of exiting through an edge and coming back through the same edge. And it's really, really simple to check. So do that first. First step, check connectivity. And you can really eyeball it. Orientability is hard to see on the surface. So it's either this picture of having one side or this picture of having kind of the clock reversed if it moves around the surface. So this is quite hard to check on the surface itself, but it's really easy to check on the words. So you just do it. You just check for those edges. You make a little check marker, or you cross it out depending on whether it's orientable or not. So if it's orientable, put P equals 0, and if it's not orientable, put T equals 0. So P counts the number of projective planes. The last one is also not so hard. That's what I'm trying to say. So on the surface, it's really easy to see. It's just the number of holes in the surface. But on the polygon, it's also not so hard to see. So let's look at this polygon here. And of course, you can just run the algorithm by identifying the vertices and the edges. But what you can also do is you can just say, okay, here's an edge A, and I will wrap up this edge B here because it just goes around. Maybe I do another one. I did another one here in my little example. So here, for example, D and D, I can identify D and D. And if I identify D and D, you can already see that E and F will be wrapped up in one cycle. And this is exactly what happens. So if I identify along D, you wrap up E and F into one cycle. So E and F form one cycle. And you don't need to compute any vertices, edges, or anything. It just follows from eyeballing it on the surface. And then if you do the same, if you wrap around B, so B is the next one you identify, then C will be wrapped up in one cycle. So C is the next cycle, and A is the outside cycle. So you can easily tell, just by looking at it, that this has D equals 3. I mean, that saves you a lot of time doing that. So if you can't see it, just do it this way. Obviously, you can still run the algorithm by identifying vertices and edges, but it's way better to just see it on the surface by using the geometry of the surface. Try to see how I go from the left-hand picture to the right-hand picture, and it hopefully will make some sense. what those pictures actually mean. So I say it again, it's really useful to know what those pictures actually mean. Just identify along the various edges. And then eventually we have this main statement, and obviously I will ask you about this main statement in one form or the other. So you should know how to get the numbers d, p, and t. And yeah, just pull it up. Remember that in standard form, I will have that on the next slide, we always have either those pictures when it's non-orientable or those pictures when it's orientable. So you never have projective planes and handles mixed at the same time. And that's what we call standard. That's the standard form. So you can always bring it in this form. Here are some examples. And the D is always puncture. Several names come for the D's: punctures, boundaries, or holes. P is the projective planes or the cross caps. And T are the handles or the tori. That's why T. And remember why we did that actually is this magic formula here, that whenever you have a projective plane and you put a torus next to it, the torus turns actually into a Klein bottle, which spits out two projective planes again. So whenever you have a picture like this is not in standard form, but you can replace every little handle with two little cups, with two little projective planes by this magic formula. And that's how we can always get rid of handles. So if you end up on the left-hand side, you can go to the right-hand side by just successively getting rid of handles. So the left hand is not in standard form. So if you see the left hand, so what is the standard form of the right hand, or what is in standard form, get rid of each handle. And just cut it in half and put in two projective planes. So each handle is worth two projective planes. That's the whole point of why we were able to split into those two cases. Projective plane is very strange. If you throw a handle at it, it actually eats the handle and throws out, and puts out two projective planes again. And I had an animation for that, but I don't expect you to be able to remember how it looked like. It was a bit crazy. So that's a really strange result, but it's very, very powerful. Geometrically it's strange, but abstractly it's really simple. Torus projective plane spits out two more projective planes. And the way to form the standard words is, well, think of the right-hand side. This is one of our pictures. Make one of the holes a little bit bigger. You end up with a middle picture, right? The outside is one of the holes that I just made a little bit bigger. The other two holes are the holes that they are. And then you get a polygon form by just connecting it like this, and you actually get a polygon form on the right. So try to understand the step from here to here and from here to here. It's really, again, very useful to have both pictures in mind. And then it's easy to get a standard form by it, by just reading along the word you get. So the standard form for the holes is exactly this picture that we did all the time. So just one hole ends up in the outside, and then you have many holes at the inside, and you just connect them like this to one boundary, and you just read off the word that you get from that. In general, we have done the standard words, you just paste them together, and you get a word for the surface. And the Hebrew formula. The only point about the Hebrew formula is, so recall, eventually you will need to use this formula here. And this formula tells you exactly what I said. The more complicated the surface is, so the bigger d, p, and t, the smaller the Euler characteristic. And it's related to exactly the behavior of the Hebrew formula with respect to colorings. The only tricky point about the Hebrew formula is that you always round down. So if you end up with 9.5, it's 9. Okay, so you always round down. It's just the rule you have for Hebrew formula. Otherwise, amazing formula. Just one formula for all colorings, for all surfaces. Say it again. This formula here, which you should definitely keep in mind, implies that the bigger d, the bigger p, the bigger t, the smaller the Euler characteristic. So surfaces get more complicated, the smaller the Euler characteristic. And you can easily just get the Euler characteristic from this formula as soon as you have the standard form. Just plot in the numbers, d, p, and t. So here are three handles. So 2 minus 6 is minus 4. Very, very simple calculation. Okay, and then what we do in the exam is I show you one of those pictures, and I will ask those questions. So how many vertices, how many edges, What is the Euler characteristic? So here's one face, it's not so hard. How many free edges? Free edges give you D. It's exactly the strategy that you run. Orientability gives you T or P. And the final formula that I showed you before gives you the remaining entry. And that's exactly what will happen. There will be one picture like this, and you're supposed to determine what it is. So let's see whether we can actually, so I did it here for you, but let's see whether we can actually eyeball that. So first of all, you see here, you can always run the algorithm. Okay, so you can always run the algorithm if you're unsure. But what you can do is, you see here, sorry, not here. Again, if you wrap around D, E and wrap around C, D and E will actually form a boundary cycle. So D is immediately a 1, because the rest here is just paired. And if you think about the rest, you can do, this is just, if you clap it together, you just have a little cone type picture, and you clap B together, it just wraps up into a 3. So you can tell immediately that it is actually this picture. You don't need to, you can run the algorithm, which I've done here on this slide for you. Okay, and then here's another example. Two random looking things. Can you identify what it is? So here, for example, you can already see here a sphere again, so you can just press out by surgery, just press it out and A will disappear, and whatever remains, just try it yourself. Meaning find D, P and T, and compare what you see on those sides. Here's another sphere that you can press out, D and D, and just fold it together, and it's gone. You can get rid of the edge. It's a smaller problem you need to solve. Okay, great. So again, highly recommended. Everything in green is highly recommended. Try it yourself. Okay, my final topic. I have about 10 minutes left for my final topic. That's very sad. My favorite topic, knots. So the main point about knots, I will make this clear, is exactly what you see here. Make tables of them and kind of try to find your knot on the table. So let's have a look at knots. Again, the same type of questions. Have we seen it before? If you have seen it before, it's just so much easier to just just whatever calculate its g just because you already know that it's supposed to be whatever 2 or something. So do that, and I show you kind of the main examples you need to know. So I haven't told you in the lecture what the standard ones are, but I will do now. And another thing is, I just showed it for you on the surfaces. Sometimes you can just easily simplify the polygon you see, get a smaller polygon, and you can just have a smaller calculation. Same for knots. So can you actually simplify projections that you see? Standard question is a knot trivial. That question will appear in the exam. So we definitely want a good way to answer whether the knot is the unknot. Try to calculate crossing numbers, check whether it's alternating, check whether it's colorable. So all of these are color questions here. They're all kind of the same type. Most of the time you can actually eyeball it again. Sometimes you just need to do the calculation. But don't worry, I won't ask you for too complicated calculations of determinants. I can't do that myself anyway. But a computer can, so it's actually not so bad. And the last one, that is really, really good, and I do this a little bit careful later, and it's also the recommended exercise for this week's tutorials, is the genus. It's really easy to compute for the examples we see, and it's powerful. So the genus is trivial if and only if the knot is trivial. It's not true for anything else on this slide. So the genus is a really good way to answer actually question number 3. So here our little genus is very good to answer question number 3. And I will answer them for you in a second. Remember that just a knot is an embedding into the space, and the point was we can do everything except cutting, because cutting is a non-continuous operation. And there was a new definition of equivalence that I thrown at you, which really just means you can bend knots around. But it was not the same as for surfaces, so it's not the homeomorphism definition. So homeomorphic is wrong. All knots are homeomorphic. So that's the wrong definition for knots, because everything is just a circle. A knot is just a circle. And these are the standard ones. So you allow, the standard here means up to a small number of crossings, and that's exactly what knot theory does. it writes down a table of those knots. So we have a notation for them. The notation is usually pretty simple. The capital number is the number of crossings. The small number is, well, the number of the list. So here, for example, it's a list entry. So here you have two of them. So it's 1 and 2. And there's some kind of randomly ordered list. And you just list all of them. So crossing number, you can just see what it is. Determinant, there's some calculation involved. I just did it for you. So if you can identify your knots, you can look up this table and just say determinant is 5, and you're good. Or whatever, let's say it's this one here. Determinant is 5. So always stay at the diagram for a while. Try to see whether those are those. Genus is 2, and whatever. It's prime. It's clearly alternating. So alternating always means go over, under, over, under, over, under as you walk along the knot. And that's kind of the table of knots. For some small numbers, I really recommend to have the table, and then you just, if you see a random knot, just first compare it to one of those, because essentially it answers all the questions you want to know about, at least we want to know about the knot. So note here the genus again, the genus is 0 if and only if the knot is trivial, but two different knots can have the same genus. For example, those two and those two. And they have the same genus, but they're not the same knot. These two are distinguished by the determinant, for example. So the trefoil here, determinant, and these two are distinguished by the determinant as well. So they're all different on this table. That's the table you really would like to keep in mind. Right? Like standard graphs, standard surfaces, standard dots. Just what standard knot means is a bit more tricky because you have infinitely many different ones. But up to a certain point, let's say up to 5 crossings. These are all knots with 5 crossings. So whenever you see a 5 crossing diagram, it has to be one of them. Yeah? So there you go. The rider master moves. I definitely should show you the rider master moves again. Remember, you could sometimes really simplify your diagram, and it's really not so hard. So here are the rider master moves. And in practice, it really just means you run them on the diagram. So there will be a nice picture in a second. And there's always some kind of local move that you can apply. So here you can pull the bottom string to the other side, and it's a local move, nothing else changes. So let's see, this one is next, that's the randomizer 2, and so on and so on. You just pull it straight. So by the way, all the videos are actually online on Canvas if you want to rewatch them. So I can just stop here. So always kind of check here. If I throw at you this diagram here, you could try to see, I mean, it looks already pretty trivial, and just do the sequence. And you can answer all questions now because you know it's the knot. So whatever I do, you don't need to do any calculations anymore. You just say it's the knot, so whatever, determinant is 1 anyway. Or coloring doesn't work, or something like that. So it's really powerful to just simplify your diagrams, just from the very outset. It might get tricky, and try to understand the simplification here. So you might end up with a very, very complicated diagram of the unknot, but there are some simplification steps. I won't expect you to do those simplification steps, but maybe from here onwards, so not from here certainly, but from here onwards, it's maybe not so hard. So maybe try to understand why the diagram simplifies. And then you don't need to do any calculations. You can kind of see what's going on here. This strand, pull it underneath, and pull it out, and it simplifies itself. If you can do that, that's amazing. You save a lot of time calculating determinants or genus or anything because you know it's the unknot. So just do it. Try to simplify diagrams that you see. And there will be one example where you can simplify your diagram. Again, try to check whether they're the same. I just told you there's only one knot with 4 crossings, so they have to be the same. But maybe you can actually try to see that using the Reidemeister moves. Right? There are 4 crossings. They need to be the same. We already know there's just one knot with 4 crossings. But it's not so obvious. So maybe it's a nice little exercise to check that. And the whole point was the notion of an invariant. And maybe was a little bit confusing. The point is an invariant is something you associate to a knot. It doesn't depend on the diagram. So every diagram gives us the same answer. And the idea is if the invariant is different, so here for example the coloring, so the coloring and the genus, so the coloring gives the same answer for the figure 8 knot and the trefoil, and we can't do anything. But if the invariant is different, we know that the knots are different. And that's the whole point. So you always want to find an invariant which tells you this knot is not one of the others. This knot is not trivial. So colorability was not really good. So 3 colorability in this case, but genus actually works. And again, genus always works for distinguishing a knot from the unknot. Genus is perfect for distinguishing knots from the unknot. Okay, when we had this notion of 3 colorability, and more general, so the 3 colorability is usually easy to see that it works or not by just trying it. The higher ones are a bit trickier, so you would like to use the determinant most of the time. Sometimes you can eyeball it. There's one tricky thing which I should stress here. The monochromatic coloring is always the coloring. Oh, this is a bad color. Let me try again. The monochromatic coloring is always the coloring. In particular, and not always has P colors, but always has P. So if I ever would ask you about the number of colorings and it's a low number, smaller than P, then it can't be true because you always have the monochromatic colorings. So every knot has three colorings, every knot has five colorings or more, seven colorings or more. Just keep that in mind. The last one that we had is Seifert's algorithm, which really is pretty simple, and it calculates the genus for you. It works as follows. So you orient your knot, it has some orientation, something like this, and then you can just get rid of all the crossings by just one simple move, and it simplifies your diagram from a crossing diagram to a circle type diagram. And you simply count the number of circles in that diagram. That's the number of Seifert circles S, and the number of crossings C was given before, and you can compute the genus, which is just the number of handles of the Seifert surface, to be this simple number. It's a really simple calculation. Just do it on the diagram. I'm essentially over time, and we're about to be kicked out, so let me just run it for you for the final knot, 5-1. Have we seen it before? Yes, it has 5 crossings. No, the diagram can't be simplified. That's very sad. It's not trivial. For example, we can just compute the genus. It will be 1. We can just compute the coloring. It's a 5 coloring. In this case, it's pretty obvious. It's just 5 colors around the 5 arcs. It says crossing number 5. It's alternating and so on and so on. We just go through it. But the point is, we have seen it before, so we actually know already everything about it. So we can just do it. And let me cut here because the next lecture is already on the outside. So I just did that example here. Just do it yourself again. And I recommend to just try the other knot with 5 crossings and just do the same calculation again. Okay, thank you very much. I really hope you enjoyed topology.